So we'll discuss about the radar cross section. I have started yesterday. So it's basically a measure of the effective area of the scatterer. So once you know radar cross section, you know how much is scattering from the surface or volume area, you can understand it. It's basically a function of both the angle of incidence and the angle of observation. So if you have a different value of angle of incidence and angle of observation, radar cross section is going to change. So it's a function of both angle of incidence of the wave and angle of observation, angle at which you are observing the scattering. So larger is the cross section, larger is the scattering. And we start with the scattering from a conducting cylinder of infinite length. We find out the electric field integral equation for that, and it is basically total tensor electric field is zero, which is composed of incident electric field and scattered electric field on the conductor surface. Assume a wave is incident from infinity. It's a dmz wave, transverse magnetic z direction. So Az is zero. We'll have only Ez component of the incident field, which is a function of x and y, and is directed along the z-axis. Since the incident field is along the z-axis, incident field will induce an electric current, which is also along the z-axis, and it will produce another scattered electric field, which is also along the z-axis. In that case, our vector wave equation will simply reduce to scalar wave equation of this form. The Laplacian of Ez scattered plus k square Ez scattered is equal to j omega mu naught jz. So we want to solve this wave equation using the Green's technique. We first find out the 2D Green's function for this wave equation and find out the electric field for any arbitrary current distribution. For the Green's function, we actually assume Zz is a delta function and solve this wave equation. The solution is called the Green's function. And once you have the Green's function, you do convolution of Green's function with any arbitrary unknown current density, and then you get the scattered electric field. So first, we need to find the Green's function, which is called 2D Green's function here. For that, we assume a line source carrying time harmonic electric current of amplitude I along the z-axis. We want to find a field radiated by a line source. We can actually equivalently model the current flowing on the conductor by an equivalent line source. Since the current associated with the line source is infinitely low and is directed along the z-axis, the field induced will have only non-zero component for the z-axis, that is Ez. And you know that for cylindrical waveguide, Ez is given by this summation m going from 0 to infinity. M's are the modes of the cylindrical waveguide. We'll have infinite modes, but later on we'll see that only the zero mode, m is equal to 0 mode, will contribute to such kind of scattering analysis. So this is basically linear combination of SM1 and SM2. SM1 and SM2 are the Hankels function of first kind and second kind. Then you have exponential Jm pi and exponential minus Jm pi. Cm and Dm are unknown arbitrary constant. Em and Fm is also a non-arbitrary constant, and this is the wave which is propagating along the negative z-axis. This is the wave propagating along the positive z-axis. And you also have the second condition, k rho square plus kz square is equal to k square. This is from the wave equation. See, the line is rotationally symmetric. There is no change along the phi, so there won't be any change of the field along the phi. And along the z-axis also, this is an infinite long line, and there is no change. So in that case, Kz is 0, Cm dm will be 0 when m not equal to 0. We have already discussed this in the last class. I'm just revising it. When Kz becomes 0, K rho square is equal to K square. K square is the wave number for free space. So we also spend some time on the Hankels function. Hankels function of first kind can be expressed in terms of Bessel's function Jm plus Jym. And Hankels function of second kind Sm2 can be expressed as Jm minus Jym. This looks like Euler's theorem. So Bessel's functions are actually representation for standing waves, but Hankel's function actually represent propagating waves. That will be very clear when we consider the approximation of the Hankel's function for the large argument. When this K rho argument is very large, Hankel's function of first kind can be approximated as square root of minus 2j by pi K rho exponential j K rho minus m pi by 2. Sm2 can be approximated as square root of 2j by pi K rho exponential minus j K rho plus m pi by 2. So obviously this is a wave which is propagating along the negative rho axis. This is a wave which is propagating along the positive rho axis. So now the amplitude of the Hankel function decay is 1 by square root of K rho. We have a term 1 by K rho here, 1 by K rho square root of that in both the expression Sm1 and Sm2. That is actually the signature for cylindrical waves. We have already did a discussion on cylindrical waves in the last semester also. The phase of the oscillation depends on m. So you have a term exponential minus minus m pi by 2 exponential plus m pi by 2. The phase of rotation depends on this m. Different values of m will have different phase of rotation, phase of oscillation. So we know that Sm1 is a wave propagating in the negative rho direction and Sm2 is a wave propagating in the positive rho direction. The source is at the axis of the cylinder. So now wave is outgoing from the cylinder. We cannot have any ingoing wave when we have a source at the axis of the cylinder. So obviously the second term is possible physically. First term is not possible. So in that case, A0 becomes 0. The final expression you have for the Ez is simply B0 I0 to K rho. Once I have the electric field, I can find out the magnetic field by using the Maxwell curl equation. Curl of E is equal to minus j omega mu h. So I find out curl of E divided by minus j omega mu. I get the magnetic field. And this electric field has only one component, Ez component. So Ex and Ey is 0. E rho and E phi is 0. Only Ez is here. So you can get the expression for magnetic field simply like this. 1 by j omega mu. It will have only phi component, del by del rho or Ez K rho. So finally, the expression turns out to be 1 by j eta phi hat d0 I0 to dias K rho. So dias means you are having a derivative with respect to rho. For small values of K rho, we have a simplified expression for the I02. I02 can be expressed as 1 minus 2j by pi natural logarithm of 1.7810 K rho divided by 2. And we will require this expression for finding the Green's function, 2D Green's function. So I0 to dash K rho, by substituting the value of I0 to like this and doing the partial derivative with respect to rho, final expression you have for I0 to dash K rho is minus 2j by pi rho. So the final expression for magnetic field is 1 by j eta phi hat b0 minus 2j by pi rho. So we have a very simple expression for the magnetic field now. So now we want to use Ampere's law and try to find the Green's function, 2D Green's function. From the Ampere's law, I dot dl over a closed contour is equal to I, charge a current density, a current enclosed by that closed contour. We have the expression for H. We know what is dl. Dl is rho d theta. So finally, you can do this simple integration from 0 to 2 pi. What you get is b0 is minus eta I by 4. So we can find out what is the expression for Ez. Ez is minus eta I by 4 h naught to K rho. If I want to find a Green's function, the source should be of unit amplitude. So I will become 1. In that case, 2D Green's function finally becomes minus eta by 4 h naught to K rho. I will become 1. Once I have the Green's function, usual step, I can find out the electric field for any arbitrary current Jz by doing the convolution of the Green's function with the arbitrary current density, where rho dash is x dash except y dash y hat Obviously, rho dash is the source location. Rho is the observation location without the prime coordinates x except dash plus y by hat dash. So we can find out Ez scattered by doing convolution of the 2D Green's function with the unknown current density. So what was the wave equation? Ez incident tangential component of the electric field incident plus tangential component of the scattered electric field is equal to 0. But here we just have Ez here. So Ez is actually tangential to the surface of the cylinder. So Ez incident is equal to minus Ez scattered. The Ez scattered expression is this convolution of the 2D Green's function and the current density. And what is the Ez incident? Ez incidence is a plane waves which is coming from very far away distance. And we assume that this plane wave has only Z component. So we can write the expression for plane wave as E0 exponential minus G K dot R. K dot R will have only x and y component exponential minus j kx cos phi I plus y sin I phi. This is the wave which is incident on the infinite cylinder. Phi I is the angle of incidence. So this Ez incident is dependent on this angle of incidence. When you substitute different values of phi I, you will get different values of Ez incident. So let us apply MoM. We have the electric field integral equation. We have the electric field integral equation. I want to solve the electric field integral equation by using the method of moments. The first step in the method of moments is you approximate the unknown current density by some known basis function. Summation n going from 1 to capital N alpha n, p rho minus rho n. See, this p rho minus rho n is a pulse function centered at rho n. So you consider a circle subsection, it is small subsections, then find out, assume that there is a pulse function in every subsection. That's what we are doing. We want to find a unknown current density. Unknown current density can be expressed like this. So if we divide the contour sufficiently large number of segments, then the curved segment may be replaced by a flat segment. So we are actually having a contour which is circular in shape because this is a cylindrical reflector, cylindrical scatterer. So we are subsectioning the circumference of the circle into a small subsection. But if we have sufficiently large subsection, every small subsections can be represented as flat. Then you apply the point matching. So point matching, delta testing function, rho m of the segment, reduce the integral equation to like this. Ez incident, this is observation point rho m. And what was the integral equation? We have I0 to k rho minus rho dash. Here observation is rho m, dl dash. Then since we are doing summation n going from 1 to capital N alpha n, this will be over a 1 unit subsection. So Wn is the size of the mth segment. So this is the MoM equation you have now. So you can write it in the matrix form as Ez incident at location R1, rho 1, rho 2 up to rho n should be equal to Z11, Z12, Z1n, and so on with alpha 1, alpha 2, and alpha n. Alpha is what we are supposed to find. We know what is Z, we know what is Ez incident. Let us calculate this Z matrix. Z matrix can be calculated Zmn for the off diagonal elements is eta by 4. Integration going from rho n minus Wn by 2 to rho n plus Wn by 2. Wn is the step size of the subsection, every subsection. Rho n is the location, nth location. So I0 to k rho m minus rho dash. Rho m is the observation point, rho n is the source point, dl there. So we can apply centroidal approximation and we can do integration for this eta 2 by 4. What is the width of the subsection is Wn. You calculate the function here we are integrating, which is the Hankels function of second kind of 0 order at the location rho n. So I0 to k rho m minus rho n. So for the off diagonal elements, I use centroidal approximation and do the integration by simply multiplying the width of the subsection with the integrand calculated at the location of rho n. So this is a very simple expression now. What is Rmn here? Rmn, or distance between the source and observation point rho m and rho n, is simply square root of xm minus xn whole square plus ym minus yn whole square. For the diagonal elements, I cannot use this because rho m and rho dash are at the same location. So I cannot use this. I need to do direct integration. And in that case, Z and N diagonal elements eta by 4 I0 to K rho, rho M minus rho dash DL dash. I need to do direct integration here. Here, since the source and observation are at the same location, are within the same cell, rho M and rho dash is very small. Rho M minus rho dash is very small. In that case, K rho, rho M minus rho dash will also be very small number. We can apply the small argument approximation of the Hankels function of second kind zeroth order. What was that? It was 1 minus 2j by pi natural log of 1.78107 k rho divided by 2. So this integration is very simple. You can do the integration, then you can find out alpha vector is simply Z inverse E incident, where E incident at mth location is exponential minus jk dot r. At the mth location, it becomes exponential minus jk xm cos phi I plus ym sin phi I. Once I know where is the angle of incidence and I know what is the location of the observation point, then I can find out this E incident. So I have everything. I have Z matrix, I have E incident. I take inverse of Z matrix and multiply with E incident factor. I get the alpha vector. Once I have that, I also know what is the scattered electric field. Once I have both incident field and scattered electric field, I can find out the radial cross section, RCS, which is denoted by sigma here. Sigma is calculated at a very far away distance from the source and observation point. We assume rho is the distance between source and observation point. We assume the source and observation point are very far away. We calculate it like 2 pi rho x scattered electric field amplitude square divided by incident electric field square. Incident electric field, we have this expression. This is the expression of plane waves in the far field of the source. We have calculated scattered electric field from the MoM technique we have just mentioned before. But here you have a rho here, and we are taking limit rho tends to infinity. You might be under the impression that this function will become infinite. That is not true. What was the expression for the scattered electric field? It's a cylindrical wave. So this, you have a line source as the axis of the cylinder. That's why this field will have a variation with respect to rho in the far field, in the far away distance as 1 by square root of rho. That's a signature of cylindrical wave. So when you square it, you get 1 by rho. So this rho and rho will cancel out. That's why we have 2 pi rho here. So that's how you find a radial cross section. You can write a small program and do the simulation and find out what is the radial cross section of a cylinder. That's all for the MoM. We can wind up here.